So this is what I want to talk about today. So this is basically the outline of the decision procedure that we discussed last time for propositional modal logic, where so this is called a tableau, what we construct. And so the idea is that you are given a formula which you want to check if it is satisfiable, and then you try to construct a model. And the idea is that every time you downclose your formulas, and if there is a formula of the form diamond alpha, you actually try to construct a successor world. You try to construct a tree model, and if you succeed, the formula is satisfiable. That's the idea. So this is what we talked about last time. And so let's go over the details and make sure that that works. So you are given a formula alpha naught. Check if it is satisfiable. Yeah, this is what we are told to do. So first let's define the subformulas of a formula given alpha. What is the set of subformulas of a formula alpha is the least set of formulas containing alpha and closed under what all do you want? Remember that I've already said that we will work with the syntax where we push negations all the way inside, right? So we don't have general negation. So the syntax that we work with is P, negation P, alpha or beta, alpha and beta, box alpha, diamond alpha. So no implications, but basically Boolean formulas where you have all negations are pushed inside. So you have only literals and conjunction, disjunction, and the two modalities. So closed under alpha or beta belongs to SF of okay, I should say beta 1 or beta 2. Beta 1 op beta 2 belongs to SF of alpha, then beta 1, beta 2 subset of where this belongs to conjunction or disjunction, and then op beta belongs to SF of alpha, that's all, where this is either box, diamond. So this is the natural notion of subformulas, right? All the so another way of saying is that if you draw the tree representation of alpha, take all the subtrees, right? They are all subformulas. And it's easy to see then the number of subformulas is linear in size of alpha, right? You can have only that many subformulas. And now we have, as I said, every time we want to downclose the set, so let's say what does it mean for a set to be downclosed? So, okay, so A subset of SF of alpha is downclosed if, what are the things that we want? Well, beta 1 or beta 2 belongs to A, then beta 1 belongs to A or beta 2 belongs to A, beta 1 and beta 2 belongs to A, then beta 1, beta 2 both are contained in A, and not P belongs to A. You want propositional consistency, right? If negation P is there, I don't want P to be sitting inside as well. So this is the notion of a downclosed subset. And let's say that, so now let's fix at alpha naught to be the set of down closed subsets of, we are given the formula alpha 0, and I look at set of subformulas and collect all the down closed subsets. These are the ones I am going to work with, right? So these are called the atoms. This is just terminology. So that's why it's at. So a down closed subset is generally called an atom. Okay. So these are the atoms that you build your model with. Okay. And in general, given a subset of SF alpha naught, down closure of A is the set of all B subset of A. No, subset of SF alpha naught such that belongs to at alpha naught, since I already have it. Yeah, the down closure of A is, you're going to add a lot of things, right? The down closure of A is, A itself need not be down closed, but the down closure of A is all those all those subsets which are down closed, which contain A. Say you take A, add things to make it down closed, and there can be several, right? In general, because of disjunction, one down closed subset may have beta 1, another down closed subset may have beta 2. If I start with beta 1 or beta 2, the down closure consists of two sets, right? Is this clear? Right. So this is the down closure of A, and now I want to use this to build a model for alpha naught, right? Try to build a model for alpha naught. So what is that? How do I go about it? And so a tableau for alpha naught an alpha naught tableau is a tree. Let's call it, well, we have to call it something. It's a tree rooted, it's a rooted tree, rooted at some vertex V0, and lambda is a map from V2 at alpha. So every node is labeled by one of the atoms. This is the idea, right? That's what you're going to. So from that you will pull out a model. It makes sense, right? I want to build a model. So every element as I construct is going to be having down closed subset. So lambda is a labeling function that gives me this, such that this satisfies certain conditions. What is that? 1, alpha naught belongs to, at the root I want alpha naught to be satisfied, right? Because alpha naught is a given formula and I am trying to make it true at the root. Remember, we said modal logic of a formula is satisfiable. It's satisfiable in a tree model where that formula is satisfied at the root, right? So that's what I'm going to try and do. So this is something we want. What else do we want? Then, whenever if there is a tree edge from a vertex V to an edge V prime, some things that we want. What is that? If box alpha belongs to lambda of V, then alpha belongs to lambda of V prime. And this is very natural, right? If at a vertex V, if box alpha were to be true, then every successor must satisfy alpha, right? Box alpha belongs to lambda of V means what? In the label for vertex V, so in this tree you are going somewhere. So here is V. If you have put box alpha here, you must make sure that every successor gets alpha. That's what it is. Is this condition clear? This is again natural, right, from the semantics that we have got. And 3, whenever diamond alpha belongs to lambda of V, there exists V prime such that this again we want. If in this node in the label I put in diamond beta, there must be a successor somewhere, let's say this one, and it has beta in it. Yeah, this is the meaning of. So note that we have taken care of everything in our syntax, right? What are the formulas we have got? Propositions, negations of propositions, for which we already put in a condition. Disjunction, conjunction, we have put in conditions. And for box and diamond, I need some semantics, and that is by construction, and that's going to come from here. So we should be pretty much done. Of course, this is just a definition. We have to now give an algorithm. But pretty much everything is in place, if you see. Is this clear? How we are going about it? So now what is the algorithm going to do? Algorithm says I start with alpha naught, right? What should it do first? It's going to construct a tableau, right? If it succeeds in constructing a tableau, right? How can you fail in constructing a tableau? I'm given the formula of, yeah?
So the camera is not focused, at least for me. Yeah, now it's, it's flickering actually.
Oh.
Do others also have the same problem?
Is it flickering for you? Purandar is not able to see.
It's not in focus right now.
Oh.
It seems fine.
Okay, then it must be a problem at my end.
So maybe you have to get in again. I mean, sometimes Zoom.
Momentarily it was sharp and now it's back to. Anyway, I think it's my problem. Please carry on.
Okay, I'll try. If there is something I can do, I will do. But I don't know what to do apart from. Usually I just do a refresh on Zoom and hope that it works. Yeah. Okay, let's see if it settles down. Okay, so this is the definition of an alpha naught tableau. Now the question is, how do you go about trying to construct an alpha naught tableau? What should you do? You are starting with the formula alpha naught and you are going to try to construct a tableau. Now how can you fail in, what do I mean by trying to construct? How can I fail in constructing a tableau? Given a formula alpha naught, why shouldn't a tableau exist for alpha naught? Think of P and not P, right? Suppose your given formula was P and not P. What will happen? You try to construct a tableau. You need a rooted tree, and at the root you are supposed to have alpha naught, which is P and not P. But if P and not P is present in that label is, what have we said? It's an atom. If it's an atom, then P and not P belongs to it, then both P negation P will be in it. But then another condition says if not P is there, P should not be there. So no such atom exists, right? So I won't be able to find any atom as a label for my root. So it is in coming up with my labeling function. Of course I can build a tree, but I have to come up with a labeling function, right? I'll find that if I can take P and not P as a formula and I try to downclose it, which are all the downclose sets that will have? That will be the empty set. So in general, when I try to downclose, if I find that the downclosure is empty, I know I have discovered a contradiction, right? This is the idea. So at that point, you can't, so okay. So suppose you manage to start with that, your formula, downclosure is non-empty, you pick something. Now, whenever you grow the tree, right, whenever you put an edge, you have to satisfy this condition. So we'll ensure that. Another way you are tree might have a problem is that there is some place where in the label you are saying diamond alpha, but there is no successor. In that case also what you have got is not a tableau, right? For it to be a tableau, it must satisfy this. Because I tried to do that, in the process I found a contradiction, right? Maybe the formula was diamond P and not P. When I start with diamond P and not P, at that point there is no problem, because diamond, there is no consistency condition. But when I try to construct a successor, at that point I will have to add an edge, and there I will find P and not P and I will fail, right? I mean, diamond P and not P is not satisfiable, so that is okay. So this is really the point. So I try to, my algorithm tries to construct a tableau, and if it succeeds, formula is satisfiable. If it does not succeed, it is because the given formula was not satisfiable. Okay. So this is, of course, these are examples and we need to prove this formally. But is the idea clear? Yes, Ananya? Yeah. Okay. So let us go through the construction and you will see it is quite straightforward and it is really nice and pretty and simple idea. So how does the algo go? So step 1, you start with the given formula alpha naught, right? Consider, so if down closure of the singleton set is empty, stop, fail, right? I start with my this thing, like it's like P and not P, right? If it has a propositional contradiction, I can go home, right? Else, pick A0 belong to and define T equals and the label for V naught is A0. Yeah. Oh, there is one V naught missing here. So the tree has a singleton and lambda of V naught. Yeah. So that's your tree. It's got only one vertex, which is the root, no edge relation, and the label for that is the atom that we have picked. Okay. And in general, now what do we do? Step 2, while, and notice that this is a tableau, which is, it's not quite a tableau because this is satisfied, because E is empty, but this may not be satisfied. So in general, that's what we want to do. What we have constructed, we are constructing a tree, but that tree need not be a tableau as yet, right? Because it doesn't satisfy this condition. So that's what you have to repair. While there exists V belonging to V such that diamond alpha belonging to lambda of V such that there is no V prime with do this. Okay. While such condition, whenever there is some node and a formula, let's call it a requirement, right? This is a requirement, right? If there is a node and it says diamond alpha, but there is no successor in the tree, then it's a requirement which you must fulfill, right? Then do let B equal, this is what we said. Now I need to construct a node, right? A new node I want to add, and what is the label that I want to do? I'm going to add a node, so I must make sure that this condition is satisfied, and then I have to fulfill the particular alpha, right? So we have picked this. So define B to be all gamma such that box gamma belongs to lambda of V union alpha, right? I am going to consider a label set which must have alpha because that's what I want, and it must have the edge relation, in which case I must fulfill this condition. Therefore, take whenever box gamma is there, consider gamma. Remember, this is a finite set. So, this whole thing is a finite set. They are all subformulas of alpha, of the original alpha naught. And now, if again this is if DC of B is empty, stop fail, right? Of course, this is the case with the diamond P and not P. I came down and I find that that's a contradiction. Well, you can't do much otherwise, else pick B naught belonging to down closure of B, right? And now what is the new tree? T equals V prime, E prime, lambda prime. What is V prime? V prime is V union new node V prime. This is disjoint union. Pick a new node, right? Add a new node, and E prime is and lambda of in general V or V hat equals lambda of V if V hat belongs to V, and in the particular case it's B naught. Right? So there is only new element added. For that, the label is B0, which we have fixed, right? And for the rest, you just carry whatever lambda, and that's it. And this is something odd. Continue doing this. Yeah, that's it. While such a condition holds, continue doing this. Is this clear? Okay. Now, first observation. The algorithm always terminates. Is it clear? Why? That's because whenever we have an edge from V to V prime, there is a tree edge, we can check that modal depth of formulas in V prime is strictly less than the modal depth of formulas in V. Why? Every time I go down, my modal depth decreases. Let's see, what is modal depth? Modal depth of P equals modal depth of not P equals 0. Modal depth of alpha or beta equals max modal depth of alpha, modal depth of beta. Modal depth of box alpha equals modal depth of diamond alpha equals modal depth of alpha plus 1, right? Exactly like quantifier rank, right? And what we are saying is that, I mean, this is just loose notation. I am just saying that whenever there is a tree edge, consider any formula here, that formula is going to have modal depth less than any formula sitting up there, except for propositional case, which is 0 anyway. Yeah. So any formula here is dominated by some formula up there, right? Because I have taken I have started with this formulas which came from B. Remember, box gamma was there in lambda V, diamond alpha was there. So I looked at only modal depth for some modal formulas, took their modal subformulas, and then down closed them, right? So if there were like propositions, if for instance I had P and box alpha and diamond beta in V, what will I have in V prime? P will not come, alpha will come and beta will come. Maybe I have diamond beta 1 and diamond beta 2, I may have only one of them, right? Because every box formula I carry down and I have picked some diamond formula and I have taken it down. So is it clear? So the depth of the tree, right, is finite. In fact, the depth of the tree is exactly equal to the modal depth of the, so depth of the tree, and this is the argument for, so depth of the tree is exactly equal to the modal depth. If my algorithm succeeds and stops, right, if it fails anyway it terminates, right, there is no issue. But if it succeeds and stops, it will stop because the depth of the tree that I construct is going to be less than or equal to the modal depth of the given formula alpha naught. And what about the branching degree of the tree? That's also bounded, right? How many children can a node have? Take a vertex V. Why would I add many children to V? I am taking V. Sorry?
When there's multiple box formulas.
Multiple diamond formulas. Box formulas never bother you because all of them you will carry, right? Suppose you had, box alpha, box beta, diamond gamma 1, diamond gamma 2. Then I will put gamma 1 here, gamma 2 here, alpha, beta in both, right? That's a construction. So the number of diamond formulas will tell you how many. So how many diamond formulas can you have? Something linear in the length of the formula, right? It's just a fraction. Yeah. And therefore, so since you know that the depth is bounded and the branching is bounded, the tree is finite. So this algorithm will not go on for. If it went on forever, it will construct an infinite path. That should be clear, right? And that's the only way it will go on forever. But it cannot because the construction ensures that. So the algorithm always terminates. Either it succeeds or it fails, but it will terminate. This is good news, right? Now comes the assertion. So it's clear that it terminates. Now the question is of okay. Now suppose proposition, then if alpha naught was actually satisfiable, then your algorithm will succeed and construct a tableau. This is the claim, right? You will never ever go through the stop fail business, right? That is the only way because we know that it terminates. If it fails, it must be because initially you encountered a stop fail or somewhere down here you encountered stop fail. right? So we have to prove that that is not going to happen. How do you prove this? Let yeah, the given formula was satisfiable, it has a model. Alpha naught was true in the model at some world, right? So let's call it MW naught, right? And we might as well assume that this is a rooted tree. Because if alpha is satisfiable, it is satisfiable in a tree rooted at, right? We already proved this. Do you understand what I am saying? Alpha naught is satisfiable, therefore I pick a model, but I am allowed to pick a tree model, right? I know that alpha naught was satisfiable, then it is satisfiable in a tree rooted at W0, right? Otherwise I could unfold it and make sure that is what it is, right? So this is already there for me. Now define a map mu W to at alpha naught by, actually I should only say subformulas of alpha naught. No, 2 to the SF by mu of W is the set of all alpha belonging to subformulas I am saying take any node, any world in the given model and see which are all the subformulas that are true in that world. Now clearly if you look at formulas that are true at a world, of course they are down closed, right? Obviously it's a model, right? If that world satisfies negation P, of course it doesn't satisfy P. If it satisfied alpha beta 1 or beta 2, of course it satisfied one of them. If it satisfies the conjunction, so it's obvious, right? But now this basically means my algorithm, now let us look. We also know that alpha naught belongs to mu of W naught, right? If I look at all the formulas that are true at W0, alpha naught belongs to it, right? Obviously, because we started with a world that satisfied alpha naught, right? This is just notation. No? Alpha naught is actually true at W naught. I am just rewriting it. So this means there exists a downclosed subset, right? This set cannot be empty. If I take the downclosed subsets of alpha naught, remember this particular one DC of, yeah, this one belongs to, yeah, I am saying in particular for my algorithm, it constructs DC of alpha naught, right? That cannot be empty. There is at least one witness that is available, which this fellow tells me, right? So there is no way the algorithm will fail at this stage. Is it clear? And inductively, now, so basically what I can actually do is build a map from, let me call it H, from my tree nodes V to W. Oh, let's call this V hat or something like that, valuation. From the vertices of my tree, I build a map which I consult to the worlds. What is H of V naught? W naught, right? Now inductively, I have labeled everything, right, with some world. So when I consider a tree node of this kind, H of V is some W. right? And I already know that lambda of V is a subset of mu of W, right? It need not be actually equal. It can have some more junk, right? As far as we are concerned, that's not an issue. Whatever is the label that I have got in my algorithm is contained in the original set. That's good enough. Yeah. But I mean, we can actually keep it as equal also. The main point is that I have this map. Now, I consider this set V. So remember the diamond alpha belongs to mu of W. The model satisfies diamond alpha, right? Then the model has a successor, therefore there exists a successor which satisfied alpha, right? Now if I consider mu of W prime, what do I know? The set of all gamma such that box gamma belongs to mu of W union, actually, so I might as well keep it as equal, yeah, because I have taken only the set of subformulas. Union alpha is contained in mu of W prime. We know this, right? Whenever box gamma was true at W, all those formulas union alpha is actually contained in mu of W prime. So when I take my set B and look at the down closure of B, remember this is a mu of W prime is an atom. So when I do a down closure here, this will not be empty. This gives a guarantee that that down closed set will not be empty. Right? So therefore, my algorithm will not fail in this step either. So what we are trying to say is that if you take the tree model here, in the tree, right, if I, so there is another way of doing this whole thing, right? I start with the root, that W0. Now, the model is crazy. It might have infinitely many successors, right? We don't know. But look at the subformulas that are true here. There are only so many subformulas that are true, no? So you collapse the worlds. Actually, you can pick, assume an enumeration and pick, or collapse them. You will get some children. That's what the algorithm is doing. Okay. And you keep doing this all along. So your algorithm will never fail. Okay. So it's very easy to convince yourself that by consulting the original model, my algorithm, if alpha naught was satisfiable, there was such a model is given to me, and I use it as an oracle and keep pulling out the sets and down closures. So basically every guess that I am making is justified because one of the guesses will work, right? Which model assures me. So in case alpha naught happen to be satisfiable, my algorithm will actually construct a tableau, right? It successfully constructs the tableau. It will never get stuck and it will stop because modal depth is coming down to 0. At the leaves I have only propositional formulas and I am done. Is it clear? Okay. What about the other direction? Suppose that the algo constructs the tableau then how do you show alpha naught is satisfiable? You have to construct a model for it. Which is the model that you construct? You have to say, give a set of worlds, an accessibility relation and a valuation. T alpha naught is given. What is my model M? Well, what is the set of worlds for me? What kind of model am I constructing? I need to construct a model for alpha naught, no, to show it's satisfiable. So what kind of model do I construct? Tree model, right? That tree is the model. I mean, there is nothing to it. I don't have any work to do at all. The claim is that V with the accessibility relation E and my valuation, which unfortunately I am using V for this also, please forgive me for it. Valuation is a model where V hat of vertex is what? I have to say what propositions are true at that world. So what proposition should be true at this world? I have to define a valuation. Yes? Sorry? Yes, Ananya? No. This is for any vertex. Take any vertex V. Which are all the propositions true at that vertex, at that world? So there is a tree. Now I am pointing to an arbitrary node in the tree. At that node, which are all the propositions that are true? We have to define this somehow, right, for it to be a model. Who will tell me which propositions are true? There is something in the tableau that we have not used. Huh? Yes, Siddharth?
T alpha naught.
T alpha naught is the tree.
The formulas which are
Lambda is here.
Formulas which occur at T alpha naught.
Yeah, so the propositions that are there in the label. Lambda is giving me all the formulas at that node, right? It's a down closed set. So it's lambda of V intersection P. Whatever propositions are sitting inside it, inside lambda of V. That's the valuation, right? I mean, you don't have much choice, right? Now we have to prove that this actually is a model for this formula. So how do I do that? So, and that is the usual truth lemma that we prove, right? Claim for all tree vertices, for all V belonging to V, for all formulas alpha in the subformulas of alpha naught, right? In this model M, MV satisfies alpha if and only if alpha belongs to lambda of V. This is what we need to prove. In fact, I am going to prove in one direction. So far we have been proving only both directions. Here is a chance to prove in one direction, let me do it. If I prove this, I am done. Why? Assuming claim, we are done. Because alpha naught belongs to lambda of V naught, therefore by above, that is alpha naught is satisfiable. Yeah? So that's fine. So we need to prove this by induction. And in general, this is true in all these logics, right? We need to prove only this. But to prove this, we need to prove the more general thing, right? Because the truth of the formula at the root node depends on the truth of the formulas at its children, which depends and so on. So we might as well prove it for all of them. Okay. How do you prove that? So proof of claim by induction on structure of alpha. Alpha's basic proposition, P belongs to lambda of V, tells you that P belongs to V hat of V, says okay, alpha is of the form negation P, not P belongs to lambda of V. Then what do we know? It's a down closed set. Therefore, P does not belong to lambda of V, which means P does not belong to V hat of V, the valuation that we have defined, which means which means the vertex satisfies not P. Okay. So if negation P is there, P is not there, therefore P is not in the valuation, so P is not true in the model, therefore negation P is true in the model. Yeah. So this takes care of not P. So note that I pushed negations all the way inside, and therefore I am able to prove this in one direction. Most of the inductive proofs you have seen so far deal with full negation, that will work only in the if and only if case, right? You can't do those proofs in one direction, because if not alpha belongs to lambda of V, suppose we have to show this, then in your usual consistency arguments you will say alpha doesn't belong to it, and then you want to apply the induction hypothesis, but the induction hypothesis goes in this direction. Induction hypothesis doesn't say anything about if alpha doesn't belong to, so you can't use that. Since you push negations all the way inside, at this level we can use it, but that's about all. Okay. So I think all this is by now known, so let me take it off. Alpha is of the form beta 1 and beta 2, and this belongs to lambda of V. By down closure condition, beta 1, beta 2 belongs to lambda of V. By induction hypothesis, so this is down closure. By induction hypothesis, the model satisfies beta 1 and the model satisfies beta 2. By semantics, okay, alpha is of the form box beta, and this belongs to lambda of V. To prove the model satisfies box beta, therefore consider some successor, take any arbitrary successor. We need to prove the model satisfies beta there, but T is a tableau, so whenever V prime, we know that box gamma belongs to lambda of V implies gamma belongs to lambda of V prime, right? We know that. Therefore, in particular, beta belongs to lambda of V prime, and then by induction hypothesis this follows. Yeah, this is the condition that we have maintained, right? After all, this is the central condition that we maintain. Whenever there is an edge, if box gamma is there in the above, gamma is there in the one below. Okay. If alpha is of the form diamond beta in lambda V, well, T is a tableau. By condition 3, there exists V prime such that beta belongs to lambda of V prime. This is the third condition in the tableau construction, to say that if there is a diamond beta, there will be a successor, right? There has to be a successor, and beta belongs to it. But then by induction hypothesis, the model satisfied beta at V prime, and then this is a successor, therefore the model satisfies diamond beta at V, and we are done, right? So this completes the inductive proof and tells you that the formula is satisfiable if and only if my tableau construction succeeds, right? So that's the complete decision procedure, right? And note that so theorem, satisfiability is decidable, because alpha naught is satisfiable if and only if the tableau construction succeeds, and the tableau construction we know it terminates, so it's certainly recursive, and we have in fact shown that the tableau construction only succeeds, it succeeds giving you a model. What do we know about the model? Whose branching degree of alpha and the depth is given by the modal degree of alpha. So what is the size of the tree? Let us say branching degree is k and depth is d. What is the size of the tree?
At most k into d.
Sorry?
At most k into d.
No, alas, no. Right? Remember, if your branching degree is 2 and your depth is d, how many nodes can you have? 2 power d, right?
2 power d.
Yeah. So in general, it's going to be exponential in the size of alpha. So the size is exponential, but this is what I was saying. Now I can do an algorithm. Remember that the depth is linear. So I can look at a Turing machine, right, which non-deterministically, it's non-deterministic because remember, a lot of guesses are being made. It's a non-deterministic Turing machine, but it can explore the tree depthwise, right? And as it goes depthwise, right, I mean, I have done the algorithm in a particular way so that it just picks an arbitrary node with a requirement. There is no need to do that, right? You can always explore it completely depthwise, keeping at every point of time some requirements pending, right? So, and note that going from root to leaf, the amount of writing that I need to do, right? I have only d times whatever number of subformulas I have got, right? Each time I have a set of subformulas, I am doing down closure, right? So, and that's number is linear, like I said. So d times that many, right? So the space that I need to write down these formulas and manage this whole thing is actually polynomial, right? So this is a non-deterministic p-space algorithm. It's what you call an n-space algorithm. And since there is a theorem which says that anything for which you have a non-deterministic p-space algorithm, you also have a deterministic p-space algorithm. That is Savage's theorem. So you say it's decidable in p-space. But if that bothers you, don't worry about it. What we have got is an exponential time algorithm. At least that must be clear, right? The size of the tree is exponential, singly exponential in the size of alpha, and that you can construct, right? You can eliminate all the guesses, you can make it deterministic. How do you do that? Write the damn down closures. No, every time you got exponential time, right? Instead of guessing one, write the down closures, right? If it's empty anyway, you're going to stop. If it's non-empty, write down each of these, right? Color them, right? So every time you ticked one and went down and you fail, you backtrack to the next one, right? You got exponential time, plenty of time to sit and do all of it. So it's certainly decidable in deterministic exponential time, right? That should be very clear. I mean, I hope there is no ambiguity there at all, because you can actually write down the DC steps at every point of time and write it in some order, so that every time you fail, you go and knock off one and try the next. That's all. And if it is satisfiable, you will find one. There is no problem, right? And so you can manage your stack carefully and do this, right? But I mean, of course, if you believe that what is p space and exponential time, it's all the same thing, then it doesn't matter. But yeah, okay. Okay, so this is the main structure of decision procedure for modal logic, and now we've already proved some expressiveness results, right? I mean, box alpha implies alpha characterizes reflexive frames, box alpha implies box alpha characterizes transitive frames. If you take both, you get pre-orders, blah blah blah. We have talked about a lot of these things, right? From pre-orders, I can get partial orders, right? So now you can start asking questions like, okay, I'm not interested in just satisfiability. I want satisfiability in pre-orders. I want to check if your formula is satisfiable in a model which is a pre-order, which is a tree. Tree we already know. Checking for whether it's satisfiable in a tree we have already done, right? But what if it is, what about its satisfiability in a, yeah, I want to ensure that the frame is transitive, right? Frame is transitive, you have a bit of a problem because we, in constructing the tree model, R is not transitive, right? The way I have constructed E, it is not transitive, right? How do you modify this construction for different classes of models? Let's particularly say I'm interested in satisfiability over reflexive models. Everything is there. What would you do with the tableau construction? What is the formula that characterizes reflexivity? We had some formula, right? Yes, Ananya, you had something? How do you say that your model is reflexive? Box P implies P. So in general, box alpha implies alpha. So that means in the down closure condition, box alpha belongs to A. That's an additional condition. It's a down closure condition, right? So far the conditions that we had were only propositional. Now in addition you're going to have, if box alpha belongs to A, then alpha belongs to A. Okay? So that's something you have to do. What else? When you construct the tree, right, at the root I said right in the first step, so your tableau is no longer a tree, but it's a tree with self loops. Big deal, huh? What is the problem? At the first step, I said V naught and empty. Instead, I have to have one edge. Yeah? And then this is the root, and lambda of V naught is A naught at the first step. That's it. I mean, in general, at each step, whenever I add that vertex V prime, I'll say V prime is V union this set V prime, which is ref, and E prime is E union. So from vertex V, I add the vertex V prime, and then I put a self loop. Now I have to make sure, because I've added an edge such that if box alpha is here, then alpha is here. But that will be the case because it's there in the down closure. Remember, I'm putting a down closed set, so it's taken care of. And that's it. Everything will go through like a dream. Don't worry about it. Yeah? Everything will follow. And it must, because that's the, the construction is entirely modular, right? I mean, you've taken care of all the requirements as you go along. Okay? And now there is some joy, because sometimes for diamond beta, right, the self loop itself may do the job for you. If that node already has beta, there is not a requirement to worry about, right? If you have diamond beta in that world, and because there is a self loop guaranteed, if that already satisfied beta, you don't have to add a child. It's only because you have diamond beta but negation beta sitting inside, then you have to add. Okay. Anyway, what about transitivity? What is the formula for transitivity?
Box alpha implies box alpha.
Very good. So what do I do for down closure now? Clearly I have to mess with the down closure, right? There for reflexivity I added this. What should I have here? What is the condition that I should put in? Here the
box alpha belongs to implies box alpha belongs to.
Not implies, but then, if then, yeah. But are you justified in doing this? Remember, if box alpha is there, we are looking for subsets of subformulas of alpha naught. Box alpha is a subformula, then so is alpha. No problem. But if box alpha is a subformula, who says box alpha is a subformula? It's not, in general. So you can't throw it in as you like. Sorry only, right? So this condition is not going to work. Okay, so that's a problem. So you can't proceed with that. What? And this part is all okay. I mean, okay, we don't have reflexivity now, maybe. So I go back to that, and when I add now, but when I add an edge and then in, right, I find diamond beta is a requirement. When do you say diamond alpha is a requirement? Remember, this is a transitive frame. We have to define, you remember the condition that we wrote, right? The general tableau condition will be there, but the algorithm, suppose diamond alpha belongs to lambda of v. What should it do? It wants to add an edge. Should I look for an immediate edge in the tree? This is a transitive frame. So, if anywhere inside it, if there is an alpha, it's okay, right? If there is a reachable node which has alpha, by transitivity there is an edge to it, right? That is the whole point about the, so no problem. Yeah. So when should I call it a requirement and actually add an edge? What is very nice is that it suffices to add things at the leaf. When you are constructing the tree, pick a leaf node. If somewhere here there is diamond alpha, it's a leaf node of the tree, right? Then I need to add an edge to this. Is this clear? So I pick, and when I do this, automatically these guys are all satisfied. Do you get the idea? For requirement, what the algorithm does is to take a leaf node of the tree, of the tableau that I am constructing of the tree. If lambda diamond alpha belongs to lambda of v for this leaf node, then I add an edge in the usual fashion. You know, box gamma, then gamma, etc. Right? And then down close it. It succeeds. I put this v prime. But the moment I do this now, for the entire path, all the vertices that are there, they will all be saying diamond alpha. Remember, it's transitive. And I don't need to worry about it. In one shot, I have filled the requirements of all of them. Yeah. Of course, and I keep doing it at the tree nodes. Is it clear? Okay. But there is a different problem. What is that? What if my formula was so I start with my node. This one, my rooted tree, it will make some guess, it will have either P, it will have not P, it does not matter, right. And if you want, I will also make it reflexive, right. So, let us say that we are looking for reflexive and transitive frame, right. So, let us say P holds, I am going to add this edge, so diamond P holds, right. Now, everywhere that I reach, this formula holds. Remember, box is now transitive, so here it holds. So, in particular, diamond not P holds here. Is this clear? Remember, this is reachable from itself, so box diamond not P holds, therefore diamond not P holds. Yeah, and this entire formula again holds here. So now I do need an edge. My algorithm will construct one. And what is the formula that holds here? Well, remember box diamond P held here, so I must have diamond P here. And box diamond not P held here, so diamond not P holds here. Yeah? Remember, this is the formula true at the root for which I am trying to construct a model. Yeah? And I am trying to construct a transitive model. Right. It said diamond not P, so I must add an edge where not P will hold. And then I had box diamond P, so diamond P will get in. And I had box diamond not P, so diamond not P will get in. And of course, I put a self loop because I need to do that. So that's all okay. Now what will happen? Because there is a diamond P, I must add an edge where P holds. But then all the reachable ones are supposed to satisfy this, right? Therefore, I must have diamond P and diamond not P. Do you see what goes on? Your algorithm does not terminate. That's because you tried to construct a tree model, right? And let us not worry so much about it being reflexive and so on, that I can always remove it and still go through this, right? Box diamond says in a transitive model, wherever I reach, I see a successor that satisfies P, and wherever I reach, so this you can see it as infinitely often P and infinitely often negation P. So it's not surprising that this damn thing is generating an infinite tree. So all we had a guarantee last time was that if alpha is satisfiable, it is satisfiable in a tree model. Whoever said it's satisfiable in a finite tree model? This one is going to force infinite trees. So your tableau construction as it is given will not succeed. It succeeds for general models, when you allow all kinds of models. It succeeds when you have reflexive models, but the moment you bring in transitivity, it does not succeed because the algorithm will not terminate. But there is a simple fix to this. Like we started with the tree, right? Tableau is a tree I defined. And then already I said for reflexive models, it is not a tree but a tree with a self loop. Well, why can't you have a tableau which is a tree with back edges, right? So you're going to build a graph, right? But a particular kind of a graph. It's a tree with certain back pointers. Here, for instance, I notice that my algorithm doesn't need to go far. Actually, all I need is this. Yeah. This back pointer does the job. And in fact, of course, when I unfold it, I'll get that infinite tree, right? So there is a slight difference. The tableau is not a model. Let's be clear about it. For transitive frames, when I do, the tableau is a tree with back edges, and as I go down, modal depth in general will not decrease. Within a connected component, the modal depth is identical. If I get out of the connected component, modal depth decreases. This is all that will happen, right? Here, modal depth is identical. In general, when I take a transitive model, right, what do you know? If box alpha belongs to this, then box alpha belongs to this. If diamond alpha belongs to this, diamond beta belongs to this, then diamond beta belongs to this. If it's part of a loop, if diamond beta belongs to this, diamond beta belongs to this. Box alpha belongs to this, box alpha belongs to this. So the modal formula satisfied within a loop, right, within any cycle in a transitive model will be identical. In fact, exactly the same set of modal formulas will be satisfied in a loop. The only differences will be propositional. So your algorithm has to be a little more clever. Nothing very deep. It's exactly the same construction that we talked about, except that what you construct is not a tree, but a tree with back edges. So you show that alpha naught is satisfiable if and only if the tableau construction succeeds, exactly like that. But the tableau itself is not a model. You remember that step when alpha naught is, we defined the model, right? The model was exactly the tree, right? Now, in the case of reflexive models, you take the tableau, add self loops and call that the model. In the case of transitive ones, take the tableau, unfold it, right? Take the tree unfolding of the tableau and that will give you the model. And that's all there is to it. Nothing very, don't think there is anything mysterious. What do I mean by back pointer? We said look in the reachable nodes, right? Reachable nodes, you also look at the paths that you have come from. Anywhere if you have got a set, right? If you have got a set which has the property that box gamma belongs to this, then gamma belongs to it, and that particular alpha belongs to it, put in a back edge. Who cares, right? And that's it. That will do the job. That's all that you look for. So the condition that you are always looking for is that I am at a leaf node and this has diamond alpha. Then is there a path to some v prime from v prime here such that if box gamma belongs to this, then gamma belongs to it and alpha is there. If it satisfies that property, then put in a back edge. Because this is the only condition that I need to fulfill. The only condition that's important is that if I put an edge, that must satisfy the property that every box gamma formula that it says, then gamma must be there, right? And in addition, particular my alpha holds. And so it's really nice because there are only so many subformulas, sets of subformulas you can have, right? You are simply building a graph among them, right? Now, this is, there are also other constructions, but I just thought that you can take the existing one and modify it. And once you do this for pre-orders, you're pretty much through because from pre-orders, by unfolding, you get partial orders, right? And it gets much more complicated if you start looking at decidability for dense frames, for instance. For dense frames, what is the formula there? It's diamond alpha. That is box alpha implies box alpha. This is much more complicated. But still it turns out that this graph construction, the tableau construction that we are doing pretty much remains sort of thing that we want to do. But I don't want to go into the details of that. So I just wanted to show you this tableau construction because it's one generic technique that works for decidability of modal logics of the kind that we have been talking about. Whole lot of modal logics, decision procedure, tableau construction is always the right way to think because that will tell you how it might go. And the tableaus themselves are very often called pseudomodels because they need not be models like in the case of the transitive thing. But it's a representation of some model, right? That it's not a tree, but it's some graph. The graph itself may be a model or the tree unfolding may be the model. You have to do some work in general, but the graph in this case is directly a model for the transitive case. If you wanted a partial order model, the graph will be only a pre-order and you have to unfold it to get the partial order, right? So it depends. But the tableau construction gives you where it is decidable. The tableau is a finite pseudomodel that witnesses that the formula is satisfiable. So think of it as a witness, as a structure witnessing the satisfiability of the formula. And the size of the tableau invariably gives you the complexity of the decision procedure in a standard fashion. Now, so this is the kind of, so we already looked at the algorithmic questions like given a finite model and a formula, a labeling procedure to check whether alpha is true in the structure, and we have a satisfiability. And we have in the process shown that if alpha is satisfiable, it's satisfiable in a finite model, satisfiable in a model of bounded size, model with particular shape like a tree model, etc., etc. It's time to look at the other kind of question, which is deduction, right? What would be the kind of axioms for, if we had Hilbert style axiom, what will be the axioms for modal logic? We have already seen certain validities. We have seen validities like box, by duality, and natural question is what will be a complete set of axioms. So you would like to have a Hilbert axioms. Since we already have propositional logic contained in it, you will have some axiomatization for the propositional part. So I'll say all substitutional instances of tautologies of propositional logic. You can take them as axioms. You can put Hilbert axioms for this thing like alpha implies beta implies alpha, etc., or simply take them as axioms. Who cares, right? For instance, box P or not box P, that's valid, right? That's a substitutional instance, right? Modal substitutional instance of a tautology. P implies P, box alpha, alpha implies alpha, right? So they are all tautologies, so let's assume them. We are only interested in adding new axioms. Rules, we already have modus ponens. Yeah. So what axioms need to be added? Something like this perhaps. As usual, it's Hilbert style, so you would like it to be in an implicational form. Remember, Hilbert axioms are all in the implicational form, right? So let's try to do that with implicational form and put in axioms. Now, which axioms will you put in? How do you find axioms in Hilbert style systems? Because what is the notion of proof? The notion of proof is all as before, right? You have a set of formulas. Let's first worry only about validity, not even worry about consequence, right? I just want to show that if a formula is valid, if and only if it's derivable, right? This is what I want to do. And in a Hilbert style system, how do you go about it? Well, like I've said many times, don't add axioms. Start doing the completeness proof, and while doing the completeness proof, you will find the need for certain axioms, put that in. That's all, right? So how do you do the completeness proof? Well, there is a notion of alpha being consistent, right? Once you have an axiom system, and what you want to prove is that every consistent formula is satisfiable, right? So assume that alpha naught is a given formula which is consistent. I want to show it is satisfiable. How do I show it's satisfiable? Well, if I can build a tableau for it, I know it's satisfiable, Remember, that's what we went through, right? So what we would like is to prove that if alpha naught is consistent, then tableau for alpha naught succeeds. Yeah. Well, for it to succeed, what must happen? The down closure must succeed, right? That says alpha naught should be propositionally consistent. In the very first step, what does down closure to succeed? What does that mean? It means that as long as alpha naught is propositionally consistent, because that's all that you check. I'm not talking about reflexive models, blah blah. I'm just talking about general models, right? Because the down closure condition is if beta 1 or beta 2 is there, then beta 1, beta 2 both are there for conjunction, one of them, etc. But that's exactly the, well, now there is a form, what is the analog of atoms of alpha naught, etc. Okay, there is a very simple idea. The idea is that with propositional logic, how did we go about constructing models? We constructed model sets, right? Sets which had this property that in fact they were down closed, up closed, whatever sets, right? In the case of first order logic, we had these model sets which had these closure conditions, complete, consistent, whatever, right? And witness fulfilled, etc. Now, so basically one maximal consistent set served as a model. Now we know that one maximal consistent set is not going to be enough because you have a whole set of worlds. Each world is a maximal consistent set, right? Remember, the truth of a formula in the model reduces to membership in that set. But now the membership is not in one set. For one world W, there is a set of formulas. For another world W prime, there is a set of formulas. In fact, for every node you have, and that is given by the label, right, lambda. Now, lambda of V is going to be simply a maximal consistent set of formulas. That's all you want. And there, that's even something better that you can do. So, what we will do is to take lambda of V is a maximal consistent subset we can do that, no? Who says maximal consistent sets should be only those infinite sets? How did you do maximal consistent sets? You did this with enumerating all the formulas, adding whatever is consistent. But why must you look at all the formulas? My universe is only subformulas of alpha naught. So, there is a notion of subset of alpha naught, there is a notion of consistent subset of alpha naught, right? When do you say what is a consistent subset of subformulas? Take some subset if the conjunction of all the formulas is consistent, right? So, there is any set of formulas, whether it's finite or infinite, that being consistent is a notion that's there with respect to your system, right? You can't derive a contradiction from it, that's all. When do you say that set is maximal? Well, if I add any formula, any subformula, if I add to it, it will become inconsistent, right? So, there is a notion of maximal consistent subset of. So, the analog of atoms that we had earlier is maximal consistent subsets of SF alpha naught. And it turns out that every maximal consistent subset is down closed, right? So, that is not a problem. If a set is maximally consistent, right, then if alpha 1 and alpha 2 belongs to it, then alpha one of both will belong to it, etc. So, that is what we need to do. And once we have this, there is this extra stuff. You remember that condition that we need box gamma is there, then gamma is there. In this, we have, that is a tableau condition. We have to show that that is consistent with respect to the axiom system. Another condition was if diamond beta is there, I can construct. Now, how do you construct something? Well, you have to show that some particular set is consistent. That again will refer to the axiom system. And in the process of fixing that, showing that this set is consistent, that set is consistent, we'll add some axioms and inference rules. So when you add those axioms and inference rules, we'll be able to show that my tableau construction succeeds. And we know that if tableau construction succeeds, the formula is satisfiable. So in fact, what is very nice is that when we complete this, we get not only a completeness proof, but also a decidability proof, right? Because we are showing if alpha naught is consistent, then it has a model which is a finite tree model, right? So so that shows that alpha naught is consistent, it's satisfiable in a bounded size model. But if the other way, if alpha is satisfiable, by soundness it is consistent. So we show that alpha is satisfiable if and only if it is satisfiable in a bounded size model. That immediately gives decision procedure. Now, we already have a decision procedure. I am just saying that this is a generic technique whereby you show the completeness of the axiom system and the decidability of the satisfiability problem in one shot. So, okay. So, we will take this up. So, as it turns out, next week there is this FSTTCS conference. So, and then there are these workshops. So, Monday we will not have class. Thursday we can have class if I can skip that session and come, or if you want to attend the conference on Thursday, I will not stop you. Anybody, in which case we can simply skip next week and meet week after. Anybody, what would you prefer?
Sir, there's a workshop from 18 to 23.
The winter school, right? ISI, no, ACM winter school.
Yes, sir.
And when is this, and what are the times and so on? So maybe we can discuss on email. If there is some slot available, morning or evening, we could have the, I don't know when, I don't know the schedule of these things, right?
Yes.
So we can look at it and decide. So if you can tell me what timings are suitable, then we can fix something. Yeah?
I'll wait, sir.
Okay. So let's do it on mail then. So Monday we definitely don't have class. Thursday we could have or not, and for later also look at the schedules and decide. Yeah, because now the season starts, the festive season of conferences, workshops and schools and so on. So it's going to go now from next week until certainly middle of January, because there is a parameterized complexity thing that's going to come. There is another games workshop, several things are coming. So let's just find whatever suitable times are and try to meet. Okay?
Sir, I found it.
Bolo.
Sir, I sent the link for schedule ISLA conference.
There is a message which I have to look at. Okay. No, we'll do this on mail. I think we should not waste everybody's time now. Yeah?
Okay, sir.
Yeah, because somebody else may say something. So, we'll take it up on mail or on Slack and decide. Okay?
Okay, sir.
Oops, it's doing something. Oh, okay, it's got into something. Okay, chalo, bye then.